Yeah, so good afternoon, those joining from Europe. Good morning, those joining from the US, and good evening to those who are joining from Asia. So my name is Regina Dittmann. I'm from the Forschungszentrum Jülich, and I will share with you the seminar, the webinar about the future of high-performance computing. Are neuromorphic systems the answer? So this webinar is organized by Neuromorphic Computing and Engineering, a multidisciplinary open access journal publishing cutting-edge research on the design, development, and application of artificial neural networks and systems for both hardware and computational perspective. So scientists and engineers continue to push the boundaries of what can be achieved by artificial intelligence. So all experts agree that the current technology is still lacking of the knowledge how the world works and is lacking behind in the energy efficiency of the human brain. So today we will have a debate among 4 world experts on the field, and we will have, they will have a controversial discussion about if neuromorphic systems will be needed in the future. So we will have 4 speakers, and we will start. I would like to start this this webinar with a poll where everybody could, the audience could give their decision about neuromorphic. Will neuromorphic systems be needed or not in the beginning, so that we will know how will be how's the opinion now in the beginning of the webinar, and then finally we will have a second poll afterwards, and then we will see how good the 4 panelists did in convincing the audience. So please, we will now start the poll. Please feel free to decide about your current opinion, and afterwards we'll continue with the presentations of the panelists. Okay, so here's the, let's see. Okay, so this is a decision we have for now. Okay, you can see now the results of this. So that means at the moment we have a slight majority for yes, a few 12% for no, and there are a lot of people are undecided so far. So there's a lot of room for the panelists to convince the audience. So yeah, thanks a lot for taking part on the poll, and we will now continue with the panelists. So let me first introduce the 4 panelists to you. So we have Kwabina Boahen. He's the founder and director of Stanford's Brain and Silicon Lab. The lab develops silicon integrated circuits that emulate the way neurons compute and computational models that link neurobiophysics to cognitive behavior. This bridges neurobiology and medicine with electronics and computer science. So furthermore, we'll have Bill Daly. He's the chief scientist of NVIDIA and a professor at Stanford University. With his Stanford team, Bill developed much of the technology that is found in most large parallel computers today and previously made significant advances at MIT and CalTech. So we will have also Ralph Etienne-Cummings, who directs the Computational Sensory Motor System Laboratory at Johns Hopkins University. His research spans a range of electrical and computer engineering topics, including but not limited to mixed signal, BISL systems, computational sensors, computer vision, neuromorphic engineering, smart structures, mobile robotics, and neuroprotective devices. And finally, we'll have Yann LeCun, who is the chief AI scientist at Meta and professor at New York University. An ACM Turing Award Laureate for his research on deep learning. Yann also researches computer vision, robotics, and computational neuroscience. So we will have all presentations will be 10 minutes. And we will have no discussion after each talk. So we will have a joint discussion after the 4 presentations. And I will first give the words to the panelists themselves to fight against each other. And then the discussion will be open to the audience in the chat. So please feel free already to put your questions into the chat during the whole presentations. And we will finally, after the discussion of the panelists, ask these questions which have been raised in the chat. So yeah, I would like now to give the words to Kwabena. Please share your presentation.
Oh, yeah, good. You can hear me now. Should I start?
Yeah, right. Yeah.
Okay, so I'm going to argue that silicon brains are the future of artificial intelligence, and I'll start by describing state-of-the-art deep neural networks. This example is from OpenAI. GPT-3 is the third in a series of large language models that they've developed, starting in 2018 with GPT-1, which had 117 million parameters, to GPT-2 with 1.5 billion in 2019, and GPT-3 in 2020 with 175 billion parameters. So we've seen the height of these stacks of decoders increase from eightfold to 96 decoders, and the width increased from 16x to 12,000 dimensions. These are signals that are flowing across these from decoders to one decoder to the next, and parameters increase 1,500 to 175 billion weights. And the reason why you're seeing this aggressive scaling here is that the errors that are made in predicting the next word follow a power law. So from GPT-2 to GPT-3, weights increase 117-fold, the amount of data used to train increased 5-fold, and that total of 570-fold more flops reduced the error by 1.4-fold, okay? Here we are measuring compute in petaflops, which is 10 to the 15 floating point operations per second running for a whole day. That's 1 unit of compute here. And this asymptote here, where these different size models basically minimize the error or cross entropy loss, follows a -120 exponent. And just to sort of put that in perspective, if you increase flops by 2 to the 20, you reduce error by a factor of 2. And to the 20 is a million-fold increase in compute. And so because of this unfavorable scaling, but it is what it is, it's cost about $5 million to train GPT-3 because you had 10,000 GPUs running all out for 2 weeks. And so what we've seen is over the last couple of decades, gone from doubling the amount of compute to train these deep neural networks every 24 months to doubling every 3.4 months. And with these large language models, that compute is doubling every 2 months. And so now basically training GPT-3 releases as much carbon as 1,500 cars do in 2 weeks. And we've also seen Google's data centers use the energy they are using increase almost 4-fold in 7 years. And so this kind of resource-intensive approach to artificial intelligence is not going to deliver AI for all. It's distributed very unequitably. And my dream of having, being able to talk to my phone like I will talk to a librarian in the library to find out what I'm looking for is far from being realized right now. If we could actually do this, run these large systems on our own personal devices, it would offload data processing from the cloud, reducing its carbon footprint. It would allow us to personalize the interaction, customize it to the user, allow real-time word-by-word speech translation, for example, and it would be secure. The data acquired and kept on our phones is not vulnerable to attacks. But if you run the numbers, it's going to require like a 15-fold faster processor with a 170-fold bigger battery to run GPT-3 on your phone. Now, what I'm going to argue is that matching the brain's energy scaling would deliver AI for all. It would give us this leap in energy efficiency to allow us to distribute AI equitably and reduce its carbon footprint. And just to summarize the argument here, I'll fill in details later, but just at a high level, if you look at the way we are building chips right now in 2D and the way we are signaling across these chips with these binary signals, about half of the wires are signaling at any given time, so that's a dense activity. The energy per unit time or power consumption versus the number of units or neurons that we have in these brain-like models is going to increase quadratically, and if we go to a 3D chip and we are still using these dense binary signals, that is dropping that to the 3/2 power scaling. And if we go to 3D and we can make these signals very sparse by using a different number coding, we would be at linear scaling of energy per number of neurons. And this matches the mammalian brain, which you see here going from 100 million neurons to 100 billion, which is us. Another way of looking at this scaling, the impact of these exponents, is if we actually say, okay, we have a human brain, which is using this sort of 3D very sparse signaling, built in 3D using very sparse signaling with 86 billion neurons, and we said, okay, with that amount of power consumption, if we were just scaling at the 3/2 power, how big a brain could we build with the same amount of power consumption? And we are going to be down to 2 billion, which is the capybara's brain. And if we were scaling quadratically, it would be actually at the fly brain with 300,000 neurons. And so these exponents make a huge difference. It's a difference between running something on your phone versus in the data center. Now, if we now look at how I got these exponents, I'm going to spend a few minutes explaining that. I just start from first principles, right? We all know that work equals force times distance. An electrical signal also does work proportional to distance, right? So it's analogous to filling a hose with water, like you see here. The water corresponds to charge, the volume corresponds to capacitance, and the work that's done is charge times voltage, which, because the capacitance is increasing with distance, the charge is also increasing with distance, okay? And voltage is just energy per unit charge. And so just by applying these principles here and coming out with the layout of these 2D or 3D chips and calculating how long all these wires are and how many signals there are, you can start to figure out how the energy is going to scale as you increase the number of neurons that you have. And one way to actually reduce the exponent is to go from 2D chips we're building now to 3D skyscrapers, okay? That's going to shorten the distances, just like how commutes are shorter in Manhattan. And the memory industry actually started doing this back in 2007. And if you got one of the latest iPhones or Galaxy phones, you've got like 1 terabyte of memory on your phone, and it's made out of 8 of these memory chips. And each one of them has a stack of memory cells that's 128 layers tall, okay? But with computing, we are still here in 2D. And so if we could leverage these advances to compute in 3D, then we could get a more favorable scaling. But then there's a problem, right? But let's compare 2D versus 3D first before we get to that problem. And so if I have a network with 10 layers with 10 units in each layer, well, the connectivity, the wave matrix from one layer to the next, I could lay that out in what's called a crossbar here. And the longest wire will be about 10 units long, okay? It's proportional to the number of units in a layer. And to get a signal across all 10 crossbars, I need a wire that's about 100 units long. And notice that this is proportional to the number of neurons, total number of neurons in my network. So I have, neurons that are doing work that's proportional to the total number, and I have signals that are proportional to the total number of neurons. So that's why I get the quadratic scaling in 2D if half the neurons are sending signals. Now, I can shorten these very long wires down to like 10 if I stack these crossbars instead of tiling them. And notice that 10 is the square root of the number of neurons. So now I've reduced my scaling from quadratic to 3/2, okay? And now, but there's an issue here, okay? By basically, I'm taking this area here, which is 100 by 100, and I've reduced it to a surface area here, which is 10 by 10. So that's a 100-fold reduction in surface area to dissipate heat, but the heat that I'm generating by sending these signals around has only reduced a factor of 10. So I have a thermal problem. This 3D chip is going to overheat. The way to deal with that is, again, look at Los Angeles versus Manhattan. You got all these cars on the same route, but the passengers are taking different vehicles instead of sharing the same vehicle. In a neural network, this corresponds to sending all these signals that are sending similar information instead of just sending one signal and eliminating the redundancy. And if you look at, how many signals are necessary, right? You can figure that out by looking at how how the data is distributed, the data set is distributed in that embedding space. And this is an example of a 3D data set that lies on a 2D manifold. And so the intrinsic dimensionality will be 2. Now, if you look at ImageNet, which is used to train these vision models, you've got 150,000 pixel images, but the intrinsic dimensionality is 35. So you only need to send, or the lower bound for signals is about 35. And in GPT-3, where you've got these 12,000 signals, the intrinsic dimensionality, the data lies on a 10-dimensional manifold. And so if now, this is how a silicon brain could scale like a biological brain. Okay, you saw this data before, but now what you do is you take the L layers and stack them, and each layer has M neurons, and each neuron has M weights. But then you add an additional constraint where there's the number of signals is determined by the intrinsic dimensionality of the data set. And so now you've got one dimension in which things are constant, and the other 2 dimensions in which activity is increasing and length of wires are increasing as you make your 3D chip bigger. And so now you've got, since these 2 dimensions give you the total number of neurons, your energy is scaling like linear with the number of neurons. And that's how you match the brain scaling. So that's it. Thank you.
Yeah, thanks a lot, Kwabena. So I will hand over then to Bill.
Okay, let me stop my open.
It doesn't seem to, okay, here we go. So hopefully you're seeing my screen.
Yes.
Okay, so let me start by saying I agree with pretty much everything Kwabena said. I think we do have, an energy problem, and one thing we're working on very hard is to basically build GPUs and accelerators to make computing neural networks much more efficient. I also think that advanced packaging can help almost all approaches to neural networks, and we're constantly looking at more efficient encodings. I may even talk a little bit about that if time permits. Let me try to figure out how to advance my slides here. So let me first of all start by saying that I believe that what we build today using NVIDIA GPUs and our accelerators is neuromorphic, just as the spiking neural networks are neuromorphic, because they're all inspired by the brain. If you start with the McCulloch-Pitts neuron, it looks very much like what we have inside of GPT-3 or inside of BERT or inside of an image transformer. We've got a bunch of neurons that basically do a dot product of weights and activations, and then we apply a nonlinear activation function to that. I think that's in common of all of these different approaches. I think the real debate here is not to be neuromorphic or not. I think we all agree that neuromorphic is doing wonderful things across artificial intelligence. The real debate is whether we should be building spiking neural network chips or not. And so what this really boils down to, if you look at the sort of people who do spiking neural networks and people who do what I'll call more conventional neural networks, is four things. In conventional neural networks, we actually work very hard to encode the data efficiently. We spent a lot of time over the last decade evolving from back in our Fermi generation, everybody using FP32 to do things, going to FP16 to bfloat to TF32, and just at the ML Sys conference, we presented an encoding called VS Quant that actually does even better than either an integer or float by itself by doing scaling over very fine dimensions. But we're sort of using integer or floating point numbers scaled very appropriately as our data representation. As I'll show in a minute, that's very efficient. Spiking neural networks tend to represent activations with a pulse train. And I think that this is great if your goal is to run experiments to simulate how the brain works, to basically test theories of biology through simulation. But if your goal is to build a neural network to do language models or image segmentation or something like that, it's horribly inefficient by a factor of 2 to 3 orders of magnitude. And I'll go into some more detail on that. Then, although many people who do build spiking chips like the Intel folks do digital, most conventional neural networks are digital and the spiking networks are analog. I'll talk about why digital is the right answer there. We tend to use relatively simple activation functions for the conventional networks because they work well. ReLU or sigmoid or a few other simple nonlinear functions are typically employed. A lot of the spiking networks, again, in analogy to the brain, a real neuron is a very complex thing that integrates over time and has very complex time varying weights. And very often those are mimicked. And again, for simulation of biology, that's great. For actually doing image recognition, it's not the greatest thing. And then there's a question of what model you're running. Today, transformers have kind of taken over the world for both images and language models. We still use convolutional neural networks for many things, and the spiking people tend to have their own unique models, and I'll talk a little bit about that. But let me start with data representation. You can think of any data representation as encoding a piece of information, a distribution, into a set of bits. And the two questions you have to ask yourself is, what is the precision and what is the dynamic range? And if you look at spiking, it's really sort of a unary encoding. You're encoding a number by how many pulses occur during a given period of time. And so, let's say that we're going to have a period of time we can have from 1 to 256 spikes. That's essentially the equivalent of int 8, which can represent numbers of that same magnitude. And it has the same characteristic that the dynamic range is up to 1 to 256, and the precision is on the order of a couple percent. We can do much better with logarithmic or floating point number representations that basically, because they have error that's proportional to the magnitude at the same time, actually have much better precision. And you can trade off the dynamic range by bits between the exponent and the mantissa. The best you can do actually is from this point of view is a symbolic representation where we basically have a lookup table that is sampling our distribution densely where the distribution is dense and sparsely where the distribution is sparse. But the reasons why you don't want to do that, because it's energetically efficient for transport, but not for operations. So the other question is, how much energy does this take? And we can break the energy into two pieces. One is, how much does it take to move the data? And for the encodings where we just simply take a bit encoding and send it across, it's proportional to the number of bits. So the SIM6 is the best here. And FP16 is the worst because it's 16 bits. Spike doesn't fit on the scale. It's 50,000 on this scale. So it's off, several rooms off to the right of my screen. And the reason for that is, much as Kwabena said, electrical signals, it's like filling up a hose with water. is the energy here. And here we have to fill the hose with water and empty it, and fill it with water again and empty it. And basically every time you toggle this signal, that dissipates CV squared of energy on the wire that you're driving. And so whereas these, a typical 8-bit representation will change half of the bits, so it's changing 4 bits, which means it's toggling 2 bits. Here, to represent the average number, which is 128, we toggle 128 times, so it's 64 times as much energy as an 8-bit representation. And this is also where the Sim8 does poorly on the operation part of the scale, because we have to decode it. Looking up at the code book is expensive, and then do high precision arithmetic to actually do the operation. Now, many people have proposed building analog neural networks. Most popular here is using solid state memory technology, and at each cross point of the solid state network, storing not a 1 or a 0, but basically putting enough charge on the floating gate of that transistor to store a weight. And then you put the input activations on the word lines of that, and you measure the current on the bit lines of that, and it basically does a dot product of the weights and the activations. And those individual operations are very efficient, on the order of a couple of femtojoules per operation. But the problem is you ultimately have to move the result of that somewhere, and in either space or time. And moving it in time means storing it in memory and reading it back out. And there really aren't efficient analog memories, or it's also not very efficient to move something at very high precision in analog any distance. So movement in time or space requires converting to digital. And if you convert to digital and you want to retain precision to match, for example, the equivalent of 8-bit precision, you wind up in the range of this, half a picojoule to a picojoule per multiply accumulate to be competitive. And that winds up making it an order of magnitude less efficient than the most efficient digital neural networks to date. So the current state of the art, this is a paper that's under review right now at the VLSI Circuit Symposium. I'm showing the reference for the earlier work from our group. We actually have working in the lab right now, running BERT large with no loss of precision compared to FP32 at 120 teraops per watt. So think of this as on the order of 8 femtojoules per operation. That's what you need to compare with if you want to compare an analog or a spiking neural network, because this is what really matters if you want to avoid excessive carbon emissions to the atmosphere, is how what is your teraops per watt for weight times activation functions at a precision that gives you no loss compared to FP32. Too often people tend to compare back to a Fermi or Kepler generation GPU, which by the way is about 3 orders of magnitude worse than this. So if the goal is to get 170 times larger battery for your cell phone, all you need to do is use state-of-the-art techniques rather than running it on your ARM core. For the models, basically there's a bunch of known benchmarks for language, for speech, and then for the overall system, an organization, MLPerf, has been created so that people can compare in a level playing field who does the best on different things, from imaging to speech recognition to natural language processing. And you'll see there are entries from Intel and Xilinx, Qualcomm, and NVIDIA, but nobody has a spiking network on these because they simply don't compete on the standard benchmarks. So let me draw an analogy. I think our aircraft that we fly today, if you fly from one end of a continent to another, are aeromorphic in the sense that the pioneers of aviation, the Wright brothers and others, were inspired by watching birds, and they learned a lot about aerodynamics, about airflow over wings and lift and drag from watching birds, about control and the like. But when it came time to build an aircraft, they decided to build it from aluminum or carbon fiber and to power it with turbines rather than to build it with feathers and flapping wings. Because while they were inspired by the birds, they realized that literally mimicking what the birds do is not a very efficient way of air transport. So let me wrap up by saying that I think all the neural networks we build today are neuromorphic. So I do agree that neuromorphic machines are the future of computing. And they're neuromorphic in the sense that they're brain inspired. By observing how the brain works and moving from the McCulloch pits on to where we are today, we've made huge progress in AI. I think spiking neural networks are useful for biological simulations. If I want to take a small piece of the nervous system of some animal and understand how it works, I can probe that and then recreate it in simulation to test my theories of how that functions. But it's not a good way of building neural networks for the purpose of perception in a self-driving vehicle or a question answering system using natural language processing. The first is that spiking is a very inefficient number representation. It's 64 times worse than int8 on an energy basis. And trying to do computations in analog, if people view that as part of the spiking dogma, is 10 times more energy because of the cost of conversion. And you need to convert to move things in time or space, and you have to move them in time or space. Any computation is not completely localized. If you're going to compare against things, you need to compare against a state-of-the-art deep learning accelerator. Our magnet is currently 120 teraops per watt, not the order of 100 gigaops per watt from the Kepler Fermi generation GPUs. This is 3 orders of magnitude better, and that's, I think, the point of comparison you need to look at. And when it comes to models, I think you have to compare against well-established benchmarks. Whether it's ImageNet if you're doing image classification, a number of the BLU scores for natural language processing, and MLPerf I think nicely wraps that up, in a well-established benchmark suite. And I don't see any of the spiking networks competing there. If they actually outperformed conventional neural networks, they would be sweeping the MLPerf numbers on natural language processing, image classification, and other things. So thank you very much for your time. I look forward to the discussion part of this.
Yeah, thanks, Bill. So I will now hand over to Ralph. So you're muted, Ralph.
There.
That's
Hello.
good.
How are you guys? Hope everybody's well. I don't have a slideshow, but I will kind of try to address directly the various ideas that's been raised by both Kwabena and Bill. So I will start first by saying that neuromorphic engineering is not multiply, accumulate. It's not that. It's not about maths. It's way more than that. In fact, the dynamics, the change of signals is as important, even more important than just basically the weighting and accumulate. So to have a system that's built on mainly on maths is by my view problematic by the start, right? So that essentially to me kind of makes Bill's argument a little bit about the fact that what the GPUs do as neuromorphic a little bit less solid by my perspective. Second thing that I would say is that it is almost never the case that you would see a signal being represented as toggling of bits in a neuromorphic system, in the sense of spike, like 20 spikes means something different than than 23 spikes typically. What's usually the case is the interspike interval that matters. It's time. So the beauty of neuromorphic engineering, in the sense that of using spikes in this case, although I'm leaving that a little bit open for the moment, in using spikes, is the interspike interval, right? It's the impact of an arriving spike and the next arriving spike, as opposed to trying to, excuse me, trying to toggle spikes along the way just to represent that number. If you do what you articulated, Bill, I agree with you that it would be inefficient, but I think there are many more ways that you can take advantage of the timing in order to make more efficient signal representation that would ultimately lead to even more efficient representation. So going back a little bit now to Kwabena's perspective, that it's a 3D structure, that we have to take advantage of 3D and so on, and I completely agree with that arrangement that Kwabena has pointed out, especially now that we get into the point where we can do compute in memory, where local memory can also participate in that computation. But I think that also another element of neuromorphic engineering, I would call it 3D plus, right? Where the plus is not just the representation of the signal, but it's other signals that are also being part of the computation. And in a neurobiological sense, those other signals are in the form of neurochemicals that are bathing the networks that are part of the computation. So we see then that that we are constructing a network that is not just about the neurons anymore. We are, synapses matter. How many of them matters. The timing of those synaptic releases matter. On top of that, you've got now other representation of signal in the milieu where all the neurons and so on and synapses live, and all those together cannot be adequately represented by a more traditional digital system without doing a lot of work to get it to be represented that way, and then ultimately to gain the benefits from those implementations. So I think in the end, the final reconstruction, if you will, of a biologically real percept or decision is going to take a lot of hardware to actually try to make it happen. So the one, so with that in mind, then I see the future of computation in a slightly different manner. I see it more as a dance between biology and electronics. And what I mean by that is that we should take advantage of biological networks and take advantage of electronics networks in the same way that we've been talking about just now, and have them work together in such a way that we can take advantage of some of the representations that are just almost impossible to represent from a simulation perspective. So that means now there's a new kind of a field, well, not new, but the field is getting a little bit more traction in this notion that you can grow networks of neurons from iPS, from stem cells in the dish. You can grow mini brains or mini retinas or mini parts of the cortex. And are there ways for us then to interface with those grown networks, grown components of the nervous system, in addition to having them communicate with our electronics in order for the computation to be done? And I would argue then that if we want to get to a point where we have a large number of variables in the in the network that is being computed, there is very few other implementations that we could do that would have the 3D structure that Kwabena articulated, and the interactions between the different elements of computation, as well as the chemicals, as well as all these other aspects that we tend to ignore entirely in our neural networks and our kind of model of AI. That is where we would maybe benefit from having really the next phase of supercomputers. I also believe that at the point where we are going to benefit from supercomputers and making sure that that we are developing these machines that can compute at the same type of accuracy, if you will, or sophistication as we have in humans and animals, is that it's going to have to be a place where we are building prosthetic devices, or we're building medicine applications of neuromorphics, where you basically have part of the nervous system being replaced by part or by some electronic or some other representation of neural systems. And to do that, you have to make them speak the same language, right? Now, the moment that you have to go between ADD conversion and D2A conversions, I think you run into a problem. So then having the nervous system and the silicon speaking the same language means operating them at the voltages that are equivalent, if you will, right? 150 millivolts or lower. And then to do that, then having them speak in spikes and having the density of interconnections and so on. So that's where I think the next step in the future comes in, right? Is what are those, those means by which you interface the artificial with the real. Essentially artificial intelligence with natural intelligence. How do you bring them together? To do that, we need to get new materials. We need to get new ways of thinking about interface and new encoding mechanism that is also maybe biologically plausible and biologically compatible, I guess is the right word. So all this is to say that that I see the future of of computing in the neuromorphic space as being a combination then of living and artificial, speaking together in a common language that is essentially going to end up being spiking language, where the third dimension can be taken advantage of, and we're not thinking about 2D chips anymore, but 3D, and then the fourth dimension being the time, but also other representational signal also being represented in our computational system, and that is where the research right now is not really touching, right? I mean, I think, and just to finish up, I think the moment that I see Intel and IBM and NVIDIA and companies of that sort getting into a field, to me means that that field is basically saturated in a sense of its growth, right? Now you're just trying to make it better and better and better, right? It's not innovative, and that's maybe my little point, little tip. But I think the innovation comes in the next form of what computation looks like. Thank you.
Yeah, thanks a lot, Ralph, for sharing your opinion. So now, finally, I would like to hand over to Yann.
All right. All right. Oops. I full screened the wrong thing. I'm sorry. All right. Okay, so should deep learning or AI hardware be neuromorphic? So first of all, I agree with a lot of what Kwabena, Bill, and Ralph have said. Probably more with what Bill says than Ralph or Kwabena. But I think we agree on what the problems are. I'm not entirely sure we see the horizon, the time horizon at which we have to solve those problems or get to that goal. Perhaps it's different. I mean, certainly for Ralph, it's different, I think. And certainly the way to get there might be different for various reasons. So let me do a little bit of history for you. And that history is, I used to work at Bell Labs, and I was in a group that was basically working on microfabrication. And the first thing they did was, they talked to John Hupfield, who at the time was at CalTech, but also part-time at Bell Labs. And John told them, you should build electronic neural nets. And so the first thing they did was build a resistor array using e-beam lithography. And it was a tiny array. They eventually made bigger ones. This was before I joined that group, a couple of years before I joined that group. Then they quickly realized that they had to connect amplifiers to those things, and the amplifiers would basically dominate the size of the entire thing, and it wasn't programmable. So the next generation chip was actually a programmable chip that had ternary weights, +1, -1, or 0, that made it somewhat flexible. And it had amplifiers and everything. But the problem there is that the chip was much faster than it could be fed from the outside. And so what happened over the next few years is that convolutional nets kind of started appearing, certainly at Bell Labs, because I joined in 1988. And so the next chip was the next two chips were actually convolution chips, and they solved the problem of feeding the chip fast enough by using shift registers, because there is a lot of data reuse in a convolution. So that's what kind of solved that problem. But there was still these were all analog. This third chip here, Net32K, was doing sort of analog products, but since it was ternary weights and binary activations, it was kind of easy. And then the sum was just a wire, right? And it could do 320 billion operations, 1 bit operations per second, which is kind of gigantic for the time. Almost simultaneously, Bernard Boser, Eddie Seckinger, and a few of us worked on the NA chip, which was basically a ConvNet chip. It was really designed to implement convolutional nets. And this one used 6-bit weights because we figured we could quantize the weights on 6 bits and the states on 3 bits, at least for things like LoNet 1 to 5, and it would still work fine. And this could do 4 billion operations per second. So this is, there's a long history, but what you see is an evolution from completely analog to partly digital to, mostly digital with a little bit of analog inside. And so in fact, what happened here is that the last chip, the NA chip, was using multiplying digital to analog converters for the multipliers, and stored the weights on capacitors. And there's an issue with this, which is that you have to make the capacitors kind of big if you want to store voltages to any kind of precision and be able to refresh them from the outside, like a dynamic RAM, basically. But then then the AT&T split up, and so the whole group was disbanded. But the hardware people, Eddie Seckinger in particular, continued working on what at first was neural net chips that were fully digital. They were basically kind of MIMD DSPs with sort of 16-bit vector instruction. That chip ended up not being used for neural nets, but it ended up being used for things like signal processing for cell phone towers and this kind of stuff, and video compression, that kind of stuff. And it came very close to what general purpose GPUs are doing today. I stopped doing hardware for a while, but then kind of revived this when people started to get interested in convolutional nets again. And so we worked on this thing called NewFlow, which was data flow architecture in the late 2000s and early 2010s. Eventually, a chip was designed around this by Eugenio Curricello's group at Purdue, but it wasn't actually able to test it. But the reason I'm telling you this is because eventually we collaborated with Bernabé Linares Barranco from Spain, and we wrote this paper where we tried to compare sort of classical data flow digital implementations of convolutional nets with basically AER address event representations, spiking neuron-like implementations that Bernabé is kind of a big fan of. And as Bill was saying, it's just not in the game. It's far behind in terms of performance when you put everything together. And I have the same analogy here that Bill used. You guys some of you may know about Clément Ader. So Clément Ader was a pioneer of aviation. In France, he actually built a steam-powered airplane that took off on its own power in 1890. That was 13 years before the Wright brothers, and you never heard of him. And the reason, except for French, but you never heard of him because it was a dead end. He had copied bats. Basically, he modeled his airplane on bats, and his airplane was able to take off because he was a really good steam engine designer. But it was basically not controllable. He built a couple of those airplanes. It's still debatable whether some of them took off or not. He left a legacy though, which is that he called his airplane l'avion, and that's what we call airplanes in French, Spanish, and Portuguese. So there is a legacy there, but why is it that you never heard of him? I think he sort of got inspired by biology, but perhaps a little too close, and perhaps without understanding some of the basic principles that really are important for flight, things like stability and controllability and things like that. He understood something about aerodynamics, obviously. So what aspects of biological neural nets are relevant that we should try to copy, and what are the ones that we should not try to copy? So things that we don't copy are things like self-assembly, things, power source, which is basically sugar, electrobiochemical computation. This is what the brain uses, and we're not even trying to copy this. Should we copy analog synapses? The fact that synapses in the brain are essentially analog, and the question really comes down to what is the smallest, most efficient multiplier? Is it digital or not? Should we use spikes? It's a big question. They're good for transmitting sparse activations efficiently, but as Bill kind of said, they're not that great, in fact, compared to the sort of more classical alternative in sort of digital CMOS. What's interesting is that the brains of large animals use spike, but tiny animals like C. elegans, which is about 1 millimeter long and has 302 neurons, their neurons are not spiking because they don't need to transmit information very far. And so they don't need spikes. So spikes is really kind of a transmission device that biology has figured out. But is it really useful? Not clear. There are many aspects of biological neural nets that are relevant and we are copying, which is why I agree with Bill when he says that all of our hardware is neuromorphic in some way. So, we use locally connected neurons that are, pretty much well identical in convolutional nets, for example, particularly in, sort of inspired from sensory cortical areas. We use rectifications in the form of values. We use normalization, divisive normalization that we observe in V1, things like batch norm, layer norm, etc. We use associative memories that neuroscientists say, are present in the hippocampus. Memory networks and transformer-style self-attention basically are associative memory. You can write into them in one shot, so they can learn quickly. This is what all the GPTs and large language models are based on, or transformers basically. We have synapse-synapse interaction equivalent in the form of basically multiplicative interactions, which is what attention uses. One thing we don't use yet, or we use but probably not in the same way the brain does, is self-supervised learning. I mean, what is the learning algorithm of the cortex? We still don't know. It's somewhat mysterious, and it might be gradient-based. So here's a bunch of things that I think just are not relevant and should not be copied, and probably are dead ends in my opinion. Okay, and I'm going on a limb here. So I don't believe in reservoir computing. I think random weights are inefficient and don't really work for anything useful. We need to learn the weights. So that's just a way to kind of, not have to learn the weights by making a network really large. I don't believe in this approach at all. Weighted dates. A lot of people in the hardware community and neuromorphic hardware community are very fond of STDP, and some biologists also. STDP doesn't do anything useful. You can't do anything with STDP. STDP is a side effect of something complicated that we don't understand, some underlying rule that we don't understand. And we need to figure out what is this underlying rule, because if we just copy STDP, we don't get anything that's interesting. My hypothesis is that the brain probably uses some form of self-supervised learning, whatever you mean by that. Probably some sort of objective is being minimized. Almost certainly, if that's the case, the gradient of this objective is being estimated. So, we know that backprop works. We know that target propagation works, which is sort of a form of backprop. I think this is what, if we want to implement learning on chip, which I think is actually a bad idea, that's probably what we should do. There's a whole bunch of problems with analog that Bill went through in details. I think I will just focus on one, which is that in analog hardware is difficult to implement, which means that you basically need to have one physical neuron or synapse per neuron or synapse in your neural net. Otherwise, you're going to have storage, memory storage, and then kind of shuffle data through a computing engine to and from memory. And that's what really kind of consumes power and energy. So, our technology is both too big and too fast. It's not small enough that we can fit an entire neural net with sort of one physical synapse and neuron per neuron in our hardware. What digital technology allows us to do is hardware reuse. And given the speed and size of our fabrication technology, I think that's what we have to do. We have to do hardware reuse, which means we have to pump data through processing elements, essentially. Unfortunately, that's what kills us in terms of power. It's shuffling data to and from memory, even if it's local. And so to the question, can neuromorphic design be useful in the medium term? And I'm talking like, 5-10 years. I want those, assistants that Kwabena was talking about, but I don't want them in 20 years. I want them in 5 or 10 years. And And so, people are putting a lot of resources into neural net accelerators that using essentially conventional digital CMOS design. What is not conventional is things like, asynchronous clocks and dynamic voltage lowering and things like that to kind of save power. And there is a huge need for this for applications like augmented reality glasses, where you need sort of built-in AI and neural nets if you want. So a short-term future is going to be something like a RISC-V core with a variable precision neural net accelerator. I mean, I don't think we can get out of this. This is for low end, right? For high end, Bill and his friends have a lock on that, but for like training and things like that. But for sort of low end inference, this may be where the world is going. This may be the new standard for microcontrollers, and it will go into everything from AR glasses to phones, cars, robots, cameras, vacuum cleaners, toys, etc. So what are the trends in AI and deep learning? As Kwabena said, the number of synapses or connections in neural nets is growing really quickly and needs to grow quickly, because we're going to a world where we pre-train all those models using self-supervised learning, and then we sort of fine-tune it for any task that we have. And if you want a multilingual, real-time speech-to-speech translation system, it's going to have on the order of 1 trillion synapses or something like that. So we're going to train on GPU clusters or things that are similar to that, maybe TPUs or something of that flavor. And then inference on data centers would be on sort of various hardware, including digital, custom digital hardware. But then what about very low power systems for wearable devices, mobile, embedded devices? I mean, certainly for sensor processing, you might want something that's kind of more neuromorphic. How do you get the power down for AR glasses, where you have to fit everything in the branch of your glasses? And how you run virtual assistants that are basically human-like intelligence on device? We're not anywhere near that yet, and we need a couple orders of magnitude progress for that. Okay, so last question is, will exotic technology change the landscape? And I'm really curious about this, to ask all of you, because I'm not an expert. Can we make synapses small enough with new technology that an entire functional neural net will fit on a single chip, while avoiding hardware multiplexing and therefore avoiding problem with storage and stuff like that? Could it be memory stiff devices? There's a lot of papers on this, over the last few years. Not clear where that's going. Could it be, graphene-based memory stirrers or whatever? Maybe that would bring the power down. Could it be spintronics? That's kind of a new thing as well. There's a lot of work there on the spintronics for neural nets. There's even those things of spin wave interference, which is sort of really kind of spooky, but somewhat interesting. Will it be holographic, optical? A convolution is basically a lens, right? So it would seem logical. There was a lot of work on this also in the 1980s. It didn't go anywhere. There's a lot of issues there that are similar to analog in terms of conversions and everything. But it's a good question to figure out, like, is there going to be some revolutionary fabrication technology or underlying technology that's going to change the landscape, would allow us to basically put a completely hardwired a useful neural net on a single chip. Thank you.
Yeah, thanks a lot, Yann, and thanks to everybody. So I found all these presentations very interesting and delighting. So and I had a feeling that there might be a lot of differences, but there was also a lot of agreement on certain points. So the question is about the bird. So which parts of the birds are crucial and which are not crucial? So furthermore, I recognize some kind of unfair situation with respect to the first speaker, because everybody else could somehow comment already on the previous speaker. So I would like, if Kwabena agrees, I would like to give the word to him to comment on his successors.
Same problem I was having, Kwabena. Finding it.
I hear you. Oh, your voice is fine for us.
Oh, I see. Good. Now it's working now. You can hear me, right?
Yes,
Yep.
yes, everything's fine.
So these were all, I'm grabbing my notes, but these were all fascinating talks, and thanks everybody for your comments and so forth. This is, of course, Yann and I go way back. I remember the days when he was making chips and he was always showing live demos in his talks. It's nice to hear about all that history, and we've all been through that history together. And I think we all know each other for decades. So it's really fun to hear everybody's perspective and so forth. And, you know, creativity comes from your personal experience. It's individual. And so we are all, you know, creating the things we do because, you know, we have a unique perspective. And I encourage people to, you know, approach that, you know, figure out what's unique about their background and follow that. And so, but the main point I want to make here, which has come up several times, is the bed versus plane analogy. And then the other point I want to make is the level of abstraction, right? And so the bird versus plane analogy, my response to that is, you know, the birds and the planes are not solving the same problem. The birds are not, they've been around for like millions of years, even billions of years, and their planet is still here. They are not making a hole in the ozone layer. They are not destroying the planet and so forth. So the planes are not solving the same problem, okay? And that comes down in our terms, that comes into the efficiency, the energy efficiency, how sustainable the approach is. And I haven't heard either Bill or Yann address the sustainability issue, neither or the equitability issue. Now, that's one on the bird side and versus the plane. And then that leads into my second point, which I've thought about a lot over the past several decades, given all this history and what we've been, what we tried and so forth, is that, you know, the way I think about the right level of abstraction is that, you know, if you look at a computer or any computing system, the things that determine the fundamental exponent with which it scales as you make the tasks more difficult, how much does your energy increase, right? That doesn't have to do with algorithms. It doesn't have to do with some sophisticated, very clever software and so forth. It has to do with the way that the hardware represents information, the primitive data representation of the hardware, and the primitive computational or the basic computational operations that the hardware is capable of. This is how you go from a problem that's exponentially hard with a conventional computer to a problem that's polynomially easy with a quantum computer by replacing ors and ands with entanglement and superposition and classical bits with quantum bits. This is just showing you that it's there. So the question really is, what are the right basic data representations that the brain is using? We should get that right. And what are the basic computational primitives that the brain is using? If we get those two things right, and we pick the right things, then we are going to be able to achieve what I call neural supremacy, like the quantum guys achieve quantum supremacy. And, you know, this came up in spikes and spike rates and so forth. I agree with Bill, spike rate is not the way to go. I think that the basic unit of information in the brain is a sequence of spikes. This is like unary signals that are representing a very high radix number. And that radix is the number of neurons in the layer. And each one, by sending a spike, can, you know, send a particular symbol. And then a sequence of spikes is giving you several digits of a n-ary number. And so this gives you the sparsity, it gives you all that you need there. And then you need something that can decode or support that representation in the hardware. And this is what dendrites are doing. They are sensitive to not just one spike, or even the weights don't matter. It's the order in which spikes come into a segment of dendrite that determines whether it responds or not by generating a plateau potential. So if I had more time, I'll get into these details, but this is what we've learned about the brain in the last 10 years, which is going to inform the next generation of neuromorphic hardware, just like we've been doing since the 40s and 50s. So thank you.
Okay, so concerning this this spike, I mean, for you, Kwabena, that was crucial to have the spiking. But in general, one could also say that perhaps the spikes are not what is useful in the birds. and then we don't have to transfer the spiking to the artificial neural networks.
Yeah,
So you would not agree on this. So you would say the spikes are key.
No, in my talk, I didn't mention spikes. You never had the word spikes.
Okay.
I said the problem here is to sparsify. And in a 3D kind of brain or 3D chip, it has to get sparser as it gets bigger, because your surface area is increasing quadratically and your heat you're generating is increasing cubically, right? And so I didn't mention spikes. It's really about the primitive data representation. You should be looking for data representation that allows you to compute in 3D. So it has to satisfy this thermal constraint. And the brain has done that. And just a spike is not a code, just like how a bit is not a code. You know, Bill mentioned like 5 different ways he can use bits to represent information. That's a code, right? And so a spike is like some signal, right? It's a signal representation, but it's not a data representation, right? And so the question is, how do you represent the information? And you know, this is the point. And I think if you pick the brain is not using, you know, there are spikes in the brain, but they are not the basic unit of information.
Okay, Ralph, you had a comment.
Pardon me?
Right.
Okay. Yeah. So I totally agree, right? I mean, in the sense that it's the ensemble that matters, right? It's not the unique notion of the spike itself. But I think there is a place where spike becomes, or at least the notion of a quantized level and time analog representation becomes very useful. And that is when our power supplies just start squeezing down on the noise flow, right? To the point where you will not have multi-levels to represent, you know, analog values, if you will, right? And the only way to represent analog values, you know, in a continuous way, is to look at inter-events. So it's not so much spikes in the classical sense, it's whatever you call an event, right? It's just that so happens that when we talk about neural networks, we tend to think about it in terms of spike. But it's that inter-event interval that matters, and also from a signal to noise perspective, a quantized level is better for represent in an environment where you have very small power supplies. You know, and you get it close to the thermal noise floor, and that's where it becomes useful.
Yeah. Can I comment on 2 things that Kwabena said? So the first is, I think we are working very hard on sustainability. So I'll take issue with that. I actually, if I could share a screen, I could show a chart here, but I'll describe it in the meantime. Where if you look at the ops, you know, per watt of a CPU, you're on the So we show screen 3 here. It's not in slideshow mode, and that's fine. Okay, pops up a little thing. Okay, you know, a CPU is a couple billion ops per watt. Just by moving to a GPU, you get about 2 orders of magnitude. That's a huge gain in sustainability. When we added tensor cores to our GPUs, which is basically hardwired accelerators to do matrix multiplies, we got another order of magnitude. And now with our very fine-tuned accelerators, you know, we're getting another order of magnitude and a half. So there's, you know, 4.5 orders of magnitude that we have gained over just doing neural networks on CPUs. I think that's a huge jump in sustainability. And I think certainly more than you would get by moving to analog or doing any of the other things that are said. So let me stop sharing. What's that?
I didn't mention the word analog in my talk.
Yeah, and let me talk about data representation, because I think that's actually key here. And I think that our goal to achieving efficiency is actually coming up with the right data representation at 2 levels. In the
but
small,
also using 3D.
Well, that's a packaging technology. I think that, you know, we may go to 3D, we may not. We're stacking memories.
You're already using it in your HBMs. You know, there's 8 chips stacked in there.
Yeah. But you know, we have to look at what, you know, that's a gain of you know, going from you know n squared to n3/2. It's not going to be huge. What is huge is coming up with representations that basically use the least amount of energy to represent the information at hand. And this happens at 2 levels. At the fine level, it's representing weights and activations. And we have found that using you know variations between integer and logarithmic representation with a small number of bits is extremely efficient at the fine scale, especially when scale factors are then applied to basically put the dynamic range where it does the most good. The other representation is really the model, right? Because it's saying at the large scale what is connected to what. And that's where I think there's a lot of room for creativity, and sparsity definitely plays in. We've worked very hard. So Yann wrote the original paper on sparse neural networks back in the 90s, but we worked very hard after sort of rediscovering it around 2015 to actually get performance out of that. And what we found is the irregularity of sparsity makes it very hard to have a sparse computation compete with a dense computation unless it's really sparse, like 0.01% dense.
Yeah, no, it's not.
But we've turned the corner on that. I mean, our Ampere GPUs have support for structured sparsity, and we're putting a lot more things in to allow us to have sparse interconnect between things, because I think being able to represent that well is key.
Mm-hmm.
Yeah, I think there's two kinds of. So first, I'm going to agree with Kwabena, connected to what you just said, Bill. There's two kinds of sparsity. One is sparsity of connections, of course, which we have to deal with in things like ConvNets and other things. But then there is sparsity of activations.
Yeah.
And right now, our hardware, as you said, does not really take advantage of this and should. And as the networks that we're using are going to get bigger, they're going to be more and more sparse, right? So the brain is about 2% activated, right? So you take any neuron at any, at some random time, it's about 2% of its sort of maximum activation range, more or less.
By the way, that's also the number for Kwabena said half the wires are toggling at any cycle in a digital chip. That's not true. I think we're running around 3% for GPU today.
Yeah, and I think the brain is far less than 2%, and it depends on the size of the brain.
Well, it depends on a lot of things. It depends also which area of the brain. Like V1 is not particularly sparse, but other areas are.
If all the wires on a GPU were to toggle every other cycle, it would melt.
Yeah,
totally. Right.
We depend on that sparse activation.
So ways to exploit, the sparse activations would be great, particularly as the networks are going to become much bigger. There has to be a way to exploit this, and then I think there's a trick that biology uses. I might be wrong about this, but the spike is only 70 millivolts, right? It's very it's very small amount of it's very small voltage, which is what Ralph was talking about, and also it doesn't propagate like when you charge the capacitor for an entire line, right? It's just like a soliton, right? That sort of propagates. Efficient energy-wise. So we haven't figured out how to do this with electronics yet, or any technology for that matter. To the sustainability question. Now there is, I think, a big misunderstanding there, which is that the total amount of energy or power that AI systems going forward are going to consume is not going to be much bigger than they currently are. Okay. And the reason for this is economics. We basically, even if we used 50 or 70%, if Meta or Google or whatever used, let's say 70% of their data centers to run neural nets, it's not the case at the moment, it's lower, but it might get there, okay, when we get sort of more sophisticated AI systems. The economics of the whole things, limits the number of data centers you can build. First of all, those data centers are all carbon neutral, so that's true for both Google and Meta. But then, you just can't kind of melt, or boil a small lake just for running AI because it's not economically feasible. And so what people are doing is that the amount of power that's consumed to run AI system is more or less constant. It grows a little, but not very quickly. But what grows is the number of operations, per joule, right? Because of the technology that Bill is talking about. And so the total amount of computation spent in AI is growing really quickly, but the amount of power, electrical power, is not. It's basically constant.
And the question, let me just address the question: is that going to continue? And I like to focus on the exponent, because you can show all these numbers, and as the networks are getting bigger, if those exponents are not favorable, you put more work. Bill has to do more and more and more work, and so that's question number one. And the last point, to address your point, is some exotic scamium technology going to do it? I don't think so. Your hardware reuse that you're talking about, that your networks are too big to fit in memory, is not true, because a 1 terabyte phone that you have now can store GPT-3's 175 billion weights with room to spare. So you can already fit it in a 3D memory chip. So the question is, 3D technology is going to deliver that number of synapses that you need. And the question is, how do you compute in 3D?
Exactly.
You want to exploit that.
Exactly.
You don't need
any of the actual.
Okay, I've got it right here. Pardon me?
Take advantage of the biology, Kwabena. That's my point, right? Take advantage of multi-layers that are already built for computation that you can tap into and use
just to
it
put it
as
in,
part of the computation.
to put it into perspective, the cortex is stacking synapses 2,000 layers deep.
Yeah.
The synapse occupies 2 by 2 by 2 microns, and it's 2 millimeters thick cortex. Right. So yeah, you need that. Okay, anyway, let me give it back to Regina.
Yes. Can't hear you.
We can't hear you.
Regina.
We can't hear you, Regina.
You're muted, Regina.
Still can't.
Still muted.
Yeah, still muted.
Yeah, there's something, it's being controlled by a higher power.
Yeah.
I have to, sorry, I have to interrupt you because there are also some questions from the audience.
Okay.
So there's a question from Steve Ferber. Brains also learn from structural plasticity. Connections come and go over time. How important is this in sparse processing systems? So who would like to answer the question?
Yeah, I think that is absolutely important. If now your representation, the basic unit of information is a sequence of spikes, and you want to actually make a segment of dendrites sensitive to a particular permutation of those spikes, that particular order, you know, that's a combinatorially huge space, right? And so you can't instantiate all those possible permutations. You have to actually rewire the system, you know, or use some kind of, in a chip, use some kind of circuit switching like in an FPGA. And so you have a spare set of connections where you can reroute them. But yeah, so I think that's absolutely, it goes with the data representation. It's not going to be matrix vector accumulate and multiply like Ralph said. It's going to be this combinatorial code, searching this combinatorial space, looking for the right permutations, and that is a whole different kind of plasticity.
And also attention.
Go ahead, Ralph.
One quick other thought. Attention is really key, right? Putting the bits where it matters. I think one of you said, I think maybe Yann said that, right, as well. So basically, you know, putting a front layer that tunes out, that does some kind of a triage, that throws out stuff that are, you know, redundant and really relevant, and only keeps information that's needed. That and in a smart way, right? In a way that is relevant to the task at hand. That's going to be a key aspect of making sure that we can reduce power and reduce, make it more sustainable.
I think Ralph said pretty much what I was going to say. The way conventional neural networks do this is with an attention mechanism. The attention mechanism today is actually a matrix multiply, but there are more efficient ways of doing an attention mechanism, which basically puts the inputs that you want, you know, into the neurons that need them.
Mm-hmm.
Yep.
Yeah, exactly.
Great.
Okay, so the next question comes from Nicolas Martin. Why human brain is so energetically efficient? Would it be possible to save energy in neuromorphic systems using only the useful neurons? So who would like to answer this question?
The main reason why the human brain is very efficient is because it's slow. If you were to sort of take a comparable number of neurons of a conventional neural network and look at the energy used to do the same kind of computation, you'd be at about the same point. In fact, you may even be a little more efficient today, but you're running way faster than real time for humans, right? Humans are going to process video at 10 frames per second or something like that. Look at typical flicker fusion frequencies, and not millions of images per second. So I think what we need to figure out is how to slow things down.
I would say, Bill, you're stuck in the cloud. You know, if I'm on the edge on my phone, I don't need to be fast. Slow is good enough for me. And if that's going to allow me to detach from the cloud, I'm very happy with that.
Yeah, but that's kind of what I said, that our technology is both too fast and too large, right? If we could slow it down somehow, and at the same time make it much more compact, the density of how neurons and dendrites are packed in the brain is ridiculous. In fact, what makes humans different from a lot of other species is that the density of neurons is much higher in primates than it is in, I don't know, dolphins or whatever, or just about anything else. And so, for example, and then the dense packing, you have V1, the primary visual cortex area, has a whole bunch of neurons. It takes input from the retina, and then it sends a lot of signals to V2. But it's not like V1 and V2 are sort of two areas on your cortex. There is actually a fold, and V1 and V2 face each other, and there's like a huge number of fibers between them. So there's a very, very short connection between those two things, and they're very close to each other because of that fold. And in fact, all the folds in the brain basically are things like that. You're connecting.
They arise like that.
Yeah. But that's my point. I mean, going back to to organoid intelligence, if you will, right? We need to take advantage of that. That to me is the exotic future, right? That to me is where we can really take advantage of some of these interconnections and do away with sorry, Bill, with the GPU scenario, and get into some real organic intelligence.
The advantage of being fast is that then you can multiplex and build small, low-power
multiplex requires you to go back and forth to memory, right? That's where you're betting your power.
You don't have to move it very far because it's already right there, right? And memory itself is not expensive. What is expensive is communication.
I agree with you 100% on that. So don't move it back and forth.
Right. Keep it local.
Okay, then the next question from Edgar Lemaire. Question to all: what do you think of event-based sensors? In this context, event-based sensors produce a very sparse representation of spatial temporal information, which could benefit to very low power processing and spiking accelerators without any conversion, so no translation costs. So this question is a little bit in line with what we discussed about sparsity, right? So who would like to comment?
Let me answer that, please. But I'm going to throw it to Yann, because Yann said something that I disagreed with in his statement, right? So Yann and I, a long time ago, worked on a project called NeoVision. And NeoVision basically was when Clément Farabert, you and Regina and so on, we were working on these image detectors and trackers, where we were essentially using a front end, which was an event-based camera, and then connecting it to the NeuroFlow stack in order to find objects and follow them and so on. In that project, we beat any other thing that was out there. In fact, our efficiency and our ability to do recognition accuracy and efficiency outperform any other group that was in that project. And so when you said that when you said that the other ones, the non-event based one won, I was a little bit confused about that, and that's what I wanted to get your perspective. What did you mean?
The work I was studying was this paper that Clément and a few people in my group and Eugenius group and Bernabé Barranco wrote, where we just did an A/B comparison, right? And there was clearly a pretty large factor in favor of kind of more traditional digital design compared to AER. Now you can always do it wrong, so okay.
It was wrong. No, just kidding.
Or you can always do it better, I should say. Okay, and it's possible that the devil is in the details, but I kind of buy Bill's argument there. So that's that there is some sort of inherent inefficiency. You basically have to wait a while before things settle when you have sort of event-based systems. So what happened, to answer the question that was asked, is that there is quite a few people working on sort of close to sensor event-based representations. And there's some argument that it's more efficient for certain applications, and that's become sort of the refugee camp of the neuromorphic community, a little bit, of people who really believed in that message, and I was one of them, early on in the 80s, certainly, from Carver-Mead's argument for it and everything, and progressively kind of interest in this has waned a little bit, and there's a few kind of defender of the crown like Ralph and Kwabena in the US. Most other people have either moved to Europe or stayed in Europe because you can get funding for this kind of stuff there. And there's been some effort, probably because the funding mechanisms are not as kind of monocultural as they are in the US, perhaps. And I think it's great. I mean, it's good for some people to work on this and sort of try to push the boundary. And again, it might come to something at some point, just not in the next 5-10 years, and perhaps it will require sort of major changes in fabrication technology, like spintronics or whatever it is, for this to happen and become practical.
Let me put a more positive spin on it. I think actually that event-based sensors are actually in use today and very successful at a coarser granularity. And I think the whole question is, what is the right granularity? So today we have smart cameras that are watching all the time, with a conventional camera chip feeding out your frames of video, a neural network sitting there watching, and only when the neural network has a detection does it bother to do the expensive thing, which is kick on the next level of neural network to say, what is that? And communicate back to home base asking for help. And so I think today at that level of granularity, event-based things are correct. And the question is, how far toward the photocell do we want to push that eventness? And right now it's not very successful to push it all the way to a given pixel activating when it sees something, but it is very successful to scan out a conventional image and have local neural network processing, which is very low power, before we do communication. So
finally, I would like to move to another topic raised by the audience, by Yulia Zadomskaya. How does the field of AI today plan to tackle the problems of ever-growing networks, energy footprint of training, rigidity of the results, problems of domains where data is scarce, etc.? Do we have a plan, or are we happy with today's success on the academic benchmarks?
We have a plan.
No.
I think we aren't happy.
My plan.
We aren't happy today. Because we do see that it takes a lot of CO2 in the atmosphere to train networks, although most people are working very hard or are already carbon neutral in the way they do it. And I think that what we're doing is we're trying to constantly strive to be more efficient, both in the hardware we run these models on and in the models themselves and the data representations. And there was a separate part of that question about data that I wasn't sure I got.
Yes,
okay, so then I have another.
I think it had to do with scarce data. So this is actually probably one of the hottest topics in sort of AI deep learning today, which is how you train very large neural nets, which are capable of doing very complex things, when you have a small amount of human annotated data. And the answer to this has been self-supervised learning. So all the large language models that have been mentioned are trained essentially with self-supervised learning, which means that you're not training them for a particular task, you're training them to represent the input. And the way you do this is you're training them to either complete an incomplete input or to predict the missing part of the input. This has worked so well in natural language processing that it's become completely standard. And that's what allowed the growth of those networks and the kind of stuff they're doing now. I mean, it's enabled revolutionary things like, you can do multilingual speech recognition, multilingual translation from a couple hundred languages to another couple hundred with a single neural net. Without having any parallel data between some of the pairs of languages, right? So that's kind of amazing. And multilingual hate speech detection on Facebook, for example, things like that, which just wasn't working nearly as well just a year or two ago. So there's been huge progress there. That progress has not yet translated into similar progress in image recognition, although progress has been really, really fast in that respect as well. But in the context of image recognition, it's not been a revolution like in the context of natural language processing, for reasons that I don't want to get into because it would be too long. But it's clear that self-supervised learning is going to also revolutionize like all aspects of machine learning. Again, for one thing to remember about the power consumption and carbon footprint, there is an enormous motivator, if you want, an enormous incentive to minimize the energy consumed per operation for running neural nets, because certainly for operators like Meta and for the suppliers like NVIDIA or others, there's an enormous incentive, which is why there are enormous engineering resources put into reducing the amount of energy and power consumed by those things. So
Yeah.
we don't need to
Thanks a
force
lot.
people to
Sorry,
do it. They just do it naturally. Okay.
Sorry, I have to interrupt you. The time is nearly over. So I thank you all. I mean, this was a very exciting discussion. But I have to finish this because we have to have the second poll and ask the audience who was now convinced. I would like to thank all of you and the audience for the great discussion and the great questions. But we will move on now to the final poll.
Thank you, guys. That was really cool.
Thank you. That was fun. Regina, thank you for moderating.
Yes, thank you.
Yeah,
Thanks,
and that was great. Thanks, everybody, for sharing your views so eloquently.
I think we convinced Yann. I think Yann is on our side now, Kwabena.
Yeah, I think Bill is the last man standing here.
Well, I'm waiting for the next revolution. You know, maybe you guys will.
Yeah,
will
I think it comes down to people are looking at different time scales. I think is it depends. That's mainly what determines where you sit.
That's true.
Mm-hmm.
I think it's a question of future. I think that's really fundamental what we're talking about. You know, future. I think what what NVIDIA does and so on is more now, and I think future is some of the more interesting structures that Kwabena talked about and I talked about. But that's my perspective.
I think we have now the results of the poll. Yeah, so the considerable amount of, I mean, the no's were constant, but the yes could convince a considerable amount of undecided audience. So yeah, great, very, very interesting. So yeah, I would like to, I have to apologize to the audience because there have been many questions, but I was unable to transfer the questions to the panelists. Nevertheless, I hope that everybody enjoyed this and had a great time. So I wish everybody good luck for the research in the future, and let's hope that AI will improve and make the step we are all waiting for in the future. Thanks a lot. Bye.
Thank you.
Thank you.
Thank you, guys. Wonderful seeing you again.
Great to see you guys.
Yeah, thanks everybody. Great to see you.
Take care.